Hello and welcome to this Caroline Cymru revision session on AS biology. Today we are going to focus on the topic of water. So this comes first of all in the first unit of AS biology 1.1, and it's the very first topic in the first unit, and it underpins quite a few of the later topics on carbohydrates, fats, and protein. So the principles we cover here we'll see again later on. Okay, so let's have a look at what we need to know about water. And the first thing we need to appreciate, and the fact that comes up repeatedly in later on in this unit, it's the idea of water being polar. So what do we mean by polar? So we describe water as a polar molecule, and polar means that whilst overall the molecule is not charged, there's an uneven distribution of charge within the molecule. So you can see the drawing I've got on there shows a water molecule, and I'm saying that overall, that part that's shaded in blue, if you like, overall that has no overall charge. It is not an ion. We know that water's H2O and there's not an ion. So it tells you it's got no overall charge. But if we look at each of the atoms that is present within water, we can see that there's ever such a slight negative charge on the oxygen atom, and there's ever such a slight positive charge on the hydrogen atoms. Now, the reason for this is something that's covered in A-level chemistry and it's not relevant in biology. I will often explain this to my pupils, though, because the bond that exists between the oxygen and the hydrogen is a covalent bond that's caused by the sharing of electrons, and that's a GCSE concept, GCSE chemistry. And so the only thing that to add on to that to make sense of why this happens is that the oxygen atom tends to hog those shared electrons a little bit more than the hydrogen atoms, or to put it differently, those shared electrons tend to spend a little bit more time near the oxygen than they do the hydrogen. And so we say the oxygen atom has a slight negative charge, and conversely than the hydrogen atoms, because they are just ever so slightly deficient of those electron presence. They're ever so slightly positively charged. And you'll see, I'll just go back a moment there, and you can see the way I've drawn that. I've put a positive, but I've also put this symbol next to it called it's a delta sign, and delta means just a little bit. You're talking a tiny fraction of the charge that would exist on an ion, but it's there. Okay, it is present. So we just say it's a little bit of positive and it's a little bit of negative. That's what the little symbol looks like, a D. Really, or sort of like an incomplete 8. It means a delta sign, delta positive, delta negative. And so when you put two water molecules near to each other, they have the capacity then to actually attract each other, because you've got a slight negative charge on the oxygen and a slight positive charge on the hydrogen, and therefore you can get a bond forming between the oxygen and the hydrogen of adjacent molecules. And it's important we say that when we talk about a bond existing between adjacent molecules, because if I just said there's a bond between an oxygen and a hydrogen, well, I'm not being clear whether I'm talking about the oxygen and the hydrogen within a water molecule, or an oxygen of one molecule and the hydrogen of another molecule. So the bond between an oxygen and a hydrogen within the molecule is a standard covalent bond. But the bond between an oxygen and a hydrogen of adjacent molecules next to each other, is called a hydrogen bond. Now it means that you can get multiple water molecules bonding to each other in this way. They're transient bonds, not especially relevant, but I'll mention what that means. Is that whereas the covalent bond within a water molecule between oxygen and hydrogen is permanent, the hydrogen bonds are temporary. So they'll form and then they'll break, and then they'll form with a different molecule between different molecules, and they'll break, and they'll form between different molecules and they'll break. But at any one time, there will be, if you imagine a huge number of water molecules, that there will be a huge number of hydrogen bonds between adjacent water molecules, which will break and reform almost immediately with a different set of water molecules. So they're constantly forming and breaking and forming and breaking. This overall idea that water molecules stick together because of these hydrogen bonds we call cohesion. And cohesion really means sort of the sticking together of like things. So cohesion is not exclusive to water. Other molecules can show cohesion. But in the context of water now, it's absolutely relevant, and we'll say that water molecules carry out cohesion. They're not the only things to do that, though. But in the context of Earth's biology, to be honest, it's the only time we'll use the term cohesion when we're talking about the sticking together of water molecules because of the hydrogen bonding between them. Okay, so let's, before we go any further, this is the sort of thing that, having been spoken to for a few minutes, it's worth just you having a little think about this yourselves. So I'll do this a couple of times, but you can pause the video now and have a little go if you can remember what those things are. And what that does, you can pause now, but what it does is it allows you to and just stop being so passive and listening and being a bit more active in this learning process and trying to come up with those answers yourselves. So what should you have on here? So this is just a regurgitation of what was written on the previous slide. So water's a polar molecule is number one. So there's an uneven distribution of charge, but there's no charge overall is number three there. Remembering that the oxygen is slightly negative in its charge, whilst the hydrogen's have a slight positive charge. When two molecules are in close contact, the opposing charges attract each other, forming a hydrogen bond. So I mentioned about some of the principles we see with water appearing later on with things like carbohydrates, fats, and proteins. Well, hydrogen bonding appears a lot. So we'll see that, or you can see that in when you look at carbohydrates even, and indeed fats and proteins. And the sticking together of water molecules we call cohesion. Okay, right. So let's have a look about why that's significant, because that's a lot of chemistry there, really. We're looking at the molecule, the water molecule, and we're looking at really how those electrons are shared there, I mentioned. Not something you'd have to regurgitate. I'll just go back, and everything you see on that page, on that slide that I'm showing you, you need to know. Okay? I talked about the covalent bond with sharing electrons. You don't need to recall that. But everything on there you need to know. But that's quite a lot of chemistry. So what we're interested in as biologists is why is it that that polar nature of water has any sort of significance in biology for biological organisms? Or perhaps that sometimes is worded as outline how the properties of water are significant for biological organisms. So there's 7 of these, and we'll deal with each of these in turn. So the first one is just simply a regurgitation of what we just said. Water is a polar molecule. So look what's written there. A slight negative charge of the oxygen, slight positive charge of the hydrogen. So hydrogen bonds form between molecules. Now, why is that relevant in biology? Well, when water is drawn up xylem vessels, you can see that when water is lost at the leaf, it pulls up, it draws up water within that xylem vessels from the root. So there's like we call it sort of a tension between the water molecules, because you're sort of pulling one side and it's drawing up water molecules from beneath it. So that polar nature itself and the hydrogen bonds and cohesion formed between the water molecules has its significance when we're thinking about xylem vessels in plants. The others are an extension of the polar nature of water. So here's an odd idea. If I was to ask you, when do you think water is most dense, a solid, a liquid, or a gas? Instinct says it would be most dense when it is a solid, when it is ice. And most molecules, like water, do indeed have their highest density when they are in their solid form. But water is odd. Water is strange. Because of the hydrogen bonds that form between molecules, it ends up that no further explanation is required here, though. It's sort of thing you could Google and see why. Um, but the key take-home message here is that, strangely, water is most dense at 4 degrees C, not 0 and below as you might expect when it's ice, but at 4 degrees C. And that means ice must be less dense than water at 4 degrees C. Therefore, ice floats. And the good thing about that is that by ice floating, the water underneath the ice is insulated from the cold, so organisms can survive underneath it. Were it the other way around, were water to be more like you would expect and like most other molecules like water, i.e. it to be solid, you'd be most dense when it is solid, ice crystals would form on the surface of water, then they would sink to the bottom, and more ice crystals would form on the surface and they would sink to the bottom, and you would get ice forming from the bottom upwards and continually forming until the whole lake, pond, whatever it may be, is frozen. There'd be no water there at all. So isn't this is significant for biological organisms because it provides this insulating layer, so organisms can survive. The other thing about water, next thing about water, is it has what we call a high specific heat. Now, the definition of specific heat is how much heat energy is needed to cause a rise in temperature. Now, we say water has a high specific heat, meaning you need loads of energy input to cause a small rise in temperature. And that's related to the hydrogen bonds between water molecules. They're restricting the movement of water molecules. But why is that significant to biological organisms? Well, it means that in aquatic environments, the temperature of the water is largely stable. So when you get hot weather, like in July, yes, the water will heat up, but not a huge amount because water has a high specific heat. And when you get really cold temperatures in December, the water will cool down, yes, but not a huge amount. Were water to have a low specific heat, in the summer, when it's hot in July, the temperature would go up to 25, 26 or higher degrees. In the winter, when it's down at -2, the temperature would go down to maybe even as low as 0 degrees. So, and imagine aquatic life wouldn't be able to deal with temperatures in the high 20s and temperatures close to freezing over the course of a year. So what they end up is a stable environment because water has a high specific heat. What else have we got? So this is the one that does not relate to the fact that water is a polar molecule, and it's probably the easiest one to remember. Water is transparent. And that means that plants that live within water are able to photosynthesize because light can pass through it. No further explanation required, very straightforward. Next thing, water is a very good solvent. And the reason water is a very good solvent is because it is polar. Molecules will dissolve in water if they are polar themselves or they are charged. And the reason for that, the reason molecules will dissolve in any solute, in any liquid, is because they are able to form associations, if you like, sort of very weak bonds with the solute, with the molecules of the solute. So the reason that sodium chloride that I'm showing on there, so sodium chloride is a substance which is made up of atoms. It's an ionic compound that when put in water, it will dissolve because the sodium ions can associate with the, because they're positively charged, they will associate with the oxygen atoms of water molecules. And you can see this diagram here that the blue there denotes the oxygen atoms. There's one of them. And notice how the way the water molecules are orientated so that the oxygen atoms are facing the inside, facing the sodium. The hydrogen atoms, which are positively charged, there's two of them on each water molecule there around the sodium, they are orientated so they are on the outside or facing away from the positively charged sodium ion. Positively charged hydrogen doesn't want to be by a positively charged sodium. Conversely, those positively charged hydrogens do want to be by the negatively charged chlorine or the chloride ion. So those hydrogen, slightly positively charged hydrogen atoms are quite happy to be facing the chloride ion, and obviously opposite then for the oxygen. Now that will apply for any charged substance, it will happily dissolve in water, and any polar molecule will happily dissolve in water for the same reason. A polar molecule will be happily dissolve in another polar, well, in a polar liquid then. So something like glucose, which is polar, happily dissolves in water. And the blood, which is largely water-based, can dissolve lots of substances within it for transport. Fantastic. So significant that water is a very good solvent. Next one, not too dissimilar to specific heat, water as a high, what we call a latent heat of vaporization. So the latent heat of vaporization is the how much energy is needed to convert from a liquid to a vapor, to convert a substance from a liquid to a gas. Okay, now water, as it turns out, again, because of its hydrogen bonding, needs a lot of energy to make that transition from a liquid to a vapor state. You'll see in this diagram here, I've shown lots of molecules that are similar to water. In order for them to evaporate, they don't need much energy at all. But water is a freak, is odd, it's very different. It needs a huge amount of energy to convert it from a liquid to a vapor state. So there's the chemistry, but what's the significant for biological organisms? It means that when we sweat, and when we sweat, the whole idea of sweating, the whole reason we sweat is that the liquid, largely water-based, is secreted onto the surface of our skin, and the heat needed to evaporate that liquid comes from our body. Now, the fact that a lot of heat energy is needed to evaporate that liquid means that a lot of heat energy is taken from our body. And the whole point of sweating is to cool us down. And therefore, water is a fantastic substance to be using in sweat because it requires an awful lot of energy to evaporate it. So an awful lot of energy is taken from our bodies, and thus we are cooled as a result of it. Last one. Water's got a high surface tension. We say it's got the highest surface tension of any liquid except for mercury, which is not really relevant, really. The mercury point is not relevant, but the fact that it's got a very high surface tension, again, it's a result of hydrogen bonding, especially on that top layer of water molecules, where you kind of get sort of double hydrogen bonding between that top layer. I've represented the water molecules here in a very regular arrangement. That is not how they appear. Water is a liquid, and therefore the molecules are not regularly arranged. But in order to sort of demonstrate this idea of sort of double hydrogen bonds on that top layer, I've drawn it in this way. What it means is that it creates this surface tension. Now, that surface tension is relevant in biology because things like pond skaters can be supported on the surface of water. Okay, so those are your seven. Those are your seven features of water that you need to be familiar with. There's quite a lot going on there. Let's do like we did previously. Let's see which of these you can reproduce. I'll go through these in a moment. But you can see it's the same idea. Rather than being passive, can you pick out what the answers to these fill in the blanks should be? So number one, water is a polar molecule. This is what we said previously. Slight negative charge to the oxygen, slight positive charge on the hydrogen. And so hydrogen bonds can form. And as I said previously, that really is the setup for most of the other features of water. Okay, the only one that doesn't apply to is the transparency of water. That's irrelevant. The hydrogen bonds factor is irrelevant. But otherwise, that first point about the polar nature of water links to every other point that's on there except the transparency. Number two, water is most dense at 4 degrees C, so ice floats and forms an insulating layer. I'm deliberately missing out what I would class as the key words here, because these are the things that would need to be regurgitated later on in questions. Water has a high specific heat, and that's defined as, and you may be asked for the definition. I think unlikely, because the focus here is more on how is that significant for biological organisms, but I have seen it asked before. Water has a high specific heat, which means a large amount of heat energy is needed to cause a small rise in temperature. And that is because those hydrogen bonds restrict the movement of molecules. So you need more heat to get them to move. And that's goes hand in hand with an increase in temperature. Water is transparent, so light can pass through to photosynthesizing plants living within it. Point number 5, or fill in the blank number 9, water is a good solvent. And a solvent is defined as something into which things can dissolve. So substances can dissolve. That means substances can dissolve in water. So as long as the solutes, the things that are to be dissolved within them, are polar or charged, they can dissolve in there. And that's because the small charges of the oxygen and hydrogen can form these weak associations with the solute. And that was significant, if you remember me talking about in blood, or indeed inside cells in the cytoplasm, which is largely water-based, and therefore molecules will dissolve in it and they can react as a result. Water's a high latent heat of vaporization. A lot of heat energy is needed to change it from a liquid to a vapor state. Talked about sweating as being the significant part of that. And water has a high surface tension, and that's relevant because it allows small insects, to be supported on its surface. Here's a little activity that's worth, again, just having a little practice with. So it involves you just pausing the video and matching up the head, what's on the left-hand side, to an appropriate tail. And you can do this just by deciding what number goes with what letter. So you might say number 1 goes with B, and number 2 goes with D, and so on. Okay, you are going to pause it, but I'll go through what we should have with this. The wording here is slightly different, but let's see how we get on. Water's, it's slightly different to what we've seen already, which is fine because it's good to see things represented in more than one way. So water is a polar molecule, meaning whilst there is no overall charge, the slight opposing charges of the atoms causes the water molecules to cohere. Cohere is not a word we've seen before, but it relates to cohesion, causes cohesion between water molecules, we could have said. Water's polar nature make it a good solvent because other molecules or charged molecules could dissolve in it, and the reason for that is because they form weak associations with the oxygen and hydrogen. Water's the second highest surface tension due to cohesion between molecules, which supports the weight of insects. Water's a high specific heat, meaning a large amount of energy is needed to cause a small temperature rise, meaning the temperature of aquatic environments is more stable. You can also refer there to the idea that inside cells, the temperature inside cells is stable. And when inside cells there's enzyme controlled reactions, we can't have temperature deviating too much. Because if it goes too high, obviously they'll denature, and if the temperature is too low, then the enzymes wouldn't function as anywhere near their optimum. 5, water's a high latent heat of vaporization, meaning a lot of energy is needed to vaporize, which is important to cool the body when sweating. 6, water's a maximum density of 4 degrees C. So ice, which is less dense, floats on the surface, allowing organisms to survive underneath. And then water is transparent, so light can pass through to photosynthesize in plants living within it. In terms of thinking about your next steps, so this is quite low level here. So when you're first learning about water, this is a nice way in. And if I just take this back to something like to this slide here, where if you were to do this activity yourself, what you would have done is you would have written down or attempted to write down the missing words. I would encourage your next step would be just to take those missing words, to blank the screen, or to look away from it, close it down, whatever it may be, and just see if you can put those words into meaningful sentences, which explains this principle of how the polar nature of water is significant for biological organisms. So you have the words polar, hydrogen, ice, insulating, etc., etc., and you would use those words then to form your own sentences to explain the significance of water for biological organisms. And that takes you up a level, because that makes you takes it up a step from fill in the blanks, which is relatively easy and a nice first step, to starting to put things in your own words and it's a greater level of understanding. So it's probably your next step. Okay, so there we are. We saw that. Let's have a look at what that might appear, how that questions might appear. And we'll do a little bit more than that here as well. We won't just look at the answer here, but we'll also look at sort of a bit of exam technique with this. So here's the question: explain how the formation of hydrogen bonds between explain the formation of hydrogen bonds between water molecules. And it says you may use annotated diagrams in your answer. Now, when I examine questions like this, as an examiner, I'm hoping that I don't have to look at a diagram. I'm hoping that I can give all the marks on what has been written, because diagrams are often quite hard to make a judgment about whether marks should be awarded. So my advice always to pupils is write your answer as if you didn't have a diagram, but then add a diagram. Because whilst you may not pick up all the marks in your writing, a diagram, adding a diagram also gives you an opportunity. They've offered you that choice. They've given you space to use a diagram. So I think it would be absolute mistake to not use a diagram, because clearly they're going to be looking for features on that diagram to award marks. So just consider that. So what should your diagram look like? Well, very similar to what I showed right at the beginning. There's a water molecule, two water molecules. They asked me to talk about the formation of hydrogen bonds, so I think it's important that I show a hydrogen bond and I label it. I just looking on that hydrogen on there. That hydrogen should be positively charged on there. That's just an error on my part to not include that. The other hydrogens are positively charged, sure. So just make sure that you're as thorough as you can with that. I've used color on this to denote the hydrogen bond. You don't have to do that. I'm really doing that to aid my explanation more than anything else. Okay. And then I'm ignoring that really, and I'm thinking, right, what am I going to write here? So this is what I put down as what I would class as a strong answer. So I'm going back, I'm just looking again at the question: explain the formation of hydrogen bonds between water molecules. So I've now said water's a polar molecule. I've then explained what that means. This means it has an uneven distribution of charge, with a slight positive charge on the hydrogen and a slight negative charge on the oxygen. This results in hydrogen bonds. They asked me to talk about hydrogen bonds, so I'm now talking about it. Hydrogen bonds forming between adjacent molecules, and this is called cohesion. Now, before we go look at it in mark scheme, let's just think about when you complete an answer, when you write an answer, you need to be gauging where you think you might be picking up marks. So you are not going to pick up marks simply by filling the space. You need to be thinking about, if you like calling them, mark scoring opportunities. Something I've said that makes me think I might get a mark there. So I've added these on here. That idea, so you can see I put it faintly in here, that the idea that water's a polar molecule, I think they haven't mentioned it in the question. So saying the word polar, I think, is going to be possibly worth a mark. It's a biological word, or if you want to call it, it's a chemistry word, if you like. But it's certainly a scientific word. Okay. Where else? So saying that what the polar means, it's got an uneven distribution of charge. I'm saying, well, I might get a mark for that, just saying what polar is. I don't know how the mark scheme is going to appear, but I might get a mark for that. I think I also might get a mark for saying that there's a slight positive charge on the hydrogen and a slight negative charge on the oxygen. So I think that's possibly going to get me a mark too. It results in hydrogen bonds between adjacent molecules. I'm thinking I'm going to get a mark there. I don't necessarily think I'm going to get the mark for the hydrogen bonds, because that has been said in the question. They said, explain the formation of hydrogen bonds. So saying hydrogen bonds are formed is not going to get me a mark. But saying that they arise between adjacent molecules, I'm thinking I might pick up a mark there. I don't know, because I don't know the mark scheme, but I'm thinking about my opportunities to score marks. And this is called cohesion. So I've mentioned cohesion, clearly a science word, a biology/chemistry specific word. So I think I could pick up a mark there. It's a 3-mark question, but I'm reasonably confident I've made 5 points that I think could get me marks. Moreover, I've got a diagram that I haven't thought about whether I'm going to pick up marks there, but I know I've got that as a backup. So based upon the fact that my knowledge is good as a student, this is what I'm thinking. My knowledge is good, so I needed to have this information ready based on the fact that my knowledge was good, and that required then the student to, then to learn my stuff well. So just having seen the slides that we've gone through so far probably isn't good enough. You need to know that, and then you're able to use it in a situation like this. Based upon that, I've given lots of detail. I haven't answered the question tentatively. I've answered it thoroughly because I know my stuff, and I've given myself 5 opportunities at least, because I don't include the diagram there, of picking up the marks. So now let's bring up what the mark scheme says. Okay, so this is the actual mark scheme. I've just sort of copy and pasted it and put it on here. And now let's see where I am picking up marks. So the first mark there is for saying that water is polar. So indeed I was correct there. I've given myself that first mark. You look at what else was on there. A dipole means just a little positive, a slightly positive, slightly negative charge. Now let's have a look at this next bit actually. So this is significant. So the hydrogen, point 2, the hydrogen positive, oxygen negative. So hydrogen slightly positive, oxygen slightly negative charges. Well, yes, I'm picking up this mark here. Okay, that's what I've said it. So it looks like I'm not getting a mark for saying there's an uneven distribution of charge, which I thought I might pick up a mark, but I am picking up the second mark down here. And so it forms bonds between hydrogen and oxygen on adjacent molecules. Now, I think I'm getting that mark. I'm reasonably confident. I haven't said on there that the bond forms between the hydrogen and the oxygen. So you might suggest perhaps I shouldn't get that. But then again, I'm going to look here at what I've got in this diagram. So on this diagram, I've shown hydrogen being slightly positive and oxygen slightly negative on the diagram. So I'm getting, at the reason I'm putting it in green to say, well, I'm not getting more marks, but I'm just confirming that I've got that mark. So had I mucked it up on my writing, my opportunity was to pick it up here. In fact, because, as I said, I made a mistake here and I didn't put the slightly positive charge on that hydrogen there, a very nasty examiner might say, no, you got the hydrogen wrong there, so I'm not giving that mark. But that's okay, because I've written it down here too. So I'm giving myself multiple opportunities to pick up the marks. And when I go back to this third point, and I say this results in hydrogen bonds forming between adjacent molecules, have I said enough there? It says forms bonds between hydrogen and oxygen on adjacent molecules. Well, I haven't said in that writing between hydrogen and oxygen, but on my diagram, I have clearly got oxygen and hydrogen. I've labeled a hydrogen bond between the oxygen and the hydrogen. So I'm confirming I'm certainly getting that. And that's a great example where that mistake I made on the hydrogen was not done on purpose. But where putting down more detail and being thorough gives you multiple opportunities to pick up the marks. And it's an excellent example of where I would say, as an examiner, if I was reading that penultimate sentence, this results in hydrogen bonds between adjacent molecules, I would be asking myself, well, can I give that mark? And I would be hoping that a diagram would allow me to give it, to confirm it. And indeed, this diagram says, lovely, there's a bond between oxygen and hydrogen. They've labeled it a hydrogen bond. I'm definitely going to give that mark now. Had that diagram not been there, that would have been a more tricky decision for me to decide whether I would have awarded that third mark. But having that diagram on there, being thorough in the answer, allows me to do that. And that is a consequence, and I'll reiterate this again, that's a consequence of knowing your content. Not just understanding, being able to regurgitate that information and knowing when to do it. So there's no way around this idea. You need to go and learn your facts. Okay, so this, what I've covered here, is not just about water. This is exam technique in here as well. I would always encourage you to just write as much as you can to pick up as many marks as you can, and consider when you've written your answer, where am I expecting to pick up marks? Not something you should expect lots of time on, expect to spend lots of time on, but it is a consideration because you need to marry up the marks being awarded and how many points you've said. It's not about how much you've written. It's about whether you've made multiple or enough marking points. You see on here that the idea of cohesion is not on the mark scheme. On another day, it might be. So I wouldn't change that. In fact, what I would probably learn from that is that I would need to emphasize that the bonding between adjacent molecules is between the oxygen of one and a hydrogen of another. That's what I've learned from that, to take that forward to my next question. Otherwise, I wouldn't change anything. I'd write everything else in there. The fact that cohesion wasn't awarded a mark this time doesn't mean I wouldn't do it next time. Okay, a slightly quicker question here. This is a very straightforward question because it's a table. You just got to again know your stuff, but they give you an awful lot here. Complete the table below, and you're welcome to pause the video and have a look. There's not a huge amount I'm going to do here with regard to an exam technique. It's more a case of going what things are on the mark scheme, and the usefulness of this is that when you look at these mark schemes, I always say you need to do the questions first. Okay, do them yourself, and then immediately check against the mark scheme, see how you did, see if you picked up the marks, but also think about what you can do better, which I emphasized on the last video. Sorry, the last slide. So why is ice less dense than water, or what is the, that's not the question, what is the biological significance of ice being less dense than water? Well, it floats on the surface. They do allow here, floats on the surface, so provides a habitat to live on. I haven't mentioned that. Maybe it's worth taking that on board. Okay, that makes sense that things like polar bears can live on ice. Okay, but more likely to see that the insulation of water underneath. So I know from experience that the second marking point is very commonly seen, and you will know from experience the more questions you do. And this is about what we mean from learning from past paper questions. The more you do, the more you start to gain an appreciation of what you would expect to see on a mark scheme. So insulation of water, so life can survive when ice forms. Life can survive beneath. Next one, what property of water has a role in cooling the body through sweating? So this is the high latent heat of vaporization. This is easier, I think, because it's knowing which is just a term that you need. The cohesion between water molecules. So that property there, now that we talked about that when we talked about that first point of the polar nature of water. What's its biological significance? Movement of water through the xylem is the first one, but they also allow you to refer to surface tension there, and that's fine. The idea that insects can live on the water surface like a pond skater, that's because of cohesion between water molecules on the uppermost layer or nearest the surface. You get more cohesion there, and that creates that surface tension. What minimizes temperature fluctuation in aquatic habitats? That's the high specific heat. They talk about high specific heat capacity there. It's fine. High specific heat is acceptable. And finally, the fact that it dissolves ionic substances. What's that property? So that means that water is a good solvent. Why is that relevant? For transport of molecules in blood, or indeed, I mentioned this, the idea that we know that chemical reactions occur in the cytoplasm, which is water-based, so you could refer to either of them then. So you can see there how we can use a past paper and a mark scheme to learn from what we might want to be referring to in the future were we to see a similar question. So this video I've put together now really is twofold, isn't it? I mean, it's the first one that appears. The first one of AS biology, water, is the very first topic you cover. And whilst I've talked about water and talked about the properties of water, I've also tried to emphasize here how you go about learning from past paper questions, and indeed a little bit of how you go about improving your understanding. By all means, use fill in the blanks, but then it needs to go up a level to put it into your own words, to start to use those terms yourselves. And then you can once you are able to recall that information, you can then go and give thorough, meaningful answers to questions, to past paper questions, and learn from what comes after that. So I hope you found that useful. You can go to the Callum Cymru website here and find other useful videos. I'm sure you'll find plenty on there for topics that you're struggling with. Thank you.